Continuing. So let's have some examples where we apply these rules. For every example, we check if it's cyclic, if it's planar, if it's completely conjugated, and if it satisfies Huckel's rule. These are all requirements that must be fulfilled in order for a compound to be considered aromatic. So, okay, previously, benzene has already been discussed as an example. Let's try this. So this is 1,3,5-hexatriene. There is no overlap. This does not form a ring. Therefore, it is not cyclic. So requirement 1, it's not fulfilled already. It is planar. It is... Wait. Sorry. There's supposed to be double bonds. This is meant to be completely conjugated. And it does satisfy Huckel's rule, since if we count the number of electrons, there are 6 electrons. So 6 qualifies, okay? Again, if you satisfy Huckel's rule, the number of electrons is any of the following, no? And the interval is 4. So like in between numbers, sorry, you basically add 4. So the next is 22, 26, 30, 34. Okay, next. How about this? 1,3-cyclohexadiene. Sorry, hexadiene. This is cyclic, number 1. Number 2, it is planar. Actually, no, it's not planar. There is some vagueness when it comes to determining if a compound is planar. That's supposedly for difficult figures. It will be specified if the compound is planar or not. But it just so happens that in this case, it is not completely conjugated. And I did mention this in the previous video, that usually when a compound is not completely conjugated, it is also not planar. I suppose this is one of the scenarios where, because it's completely conjugated, it is also not, because it is not completely conjugated, it is also not planar. And another red flag, this is not aromatic because, let's count the number of electrons, 1, 2, 3, 4. 4 electrons, is that in the list? No. So we start at 2, then 6, 10, 14, etc. So yeah, this compound isn't aromatic. Let's try 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. So this is 1,3,5-cycloheptatriene. This is cyclic. Requirement 1 is fulfilled. Number 2, is it planar? It says no. Is it completely conjugated? No. So you're confident that this is not planar. Or even if you don't really have to know if it's planar or not, because the other requirements, you found out that it is not completely conjugated, no? So that alone will already tell you that this compound isn't aromatic. But let's see if it satisfies Huckel's rule. 1, 2, 3, 4, 5, 6. 6 electrons, that is in the list, so it does satisfy Huckel's rule. But nevertheless, this is not aromatic. Let's try this example. So this is cyclooctatetraene. Is it cyclic? It is. It is not planar, and it happens to be completely conjugated. Does it follow Huckel's rule? 1, 2, 3, 4, 5, 6, 7, 8. Just count the ends of each of these lines inside. I am trying to reach out to you by simple talk, so that it's easy to understand. That's basically how you determine if a molecule, no, rather a compound, satisfies Huckel's rule. You just count the ends. So we have 8 electrons. This does not fulfill Huckel's rule. 8 is not in the list. Okay. In this example, it happens that this compound is said to be puckered. It has something to do with having a chair conformation. Regarding that, let's actually want to know. When does a compound have chair conformation? So for sure, benzene does not have. Let's verify that. Does benzene have chair conformation? I'm willing to bet it does not. That is correct. There is sp2 hybridization. I think that is the reason why this compound is completely conjugated. However, it is not fully planar. Why is cyclooctatetraene not planar? Okay, this reason isn't so helpful. Tub-shaped structure allows it to avoid being anti-aromatic. That term is something else that we have to know later. Anti-aromatic. Actually, speaking of which, what does it mean for a compound to be anti-aromatic? So it does follow all the requirements here, only that the rule it follows for number 4, the number of electrons has to be 4 or a multiple of 4. So 4, 8, 12, 16, 20, so forth. So yeah, that's the only difference between aromatic and anti-aromatic. If it's not aromatic, obviously, it is anti-aromatic if one of these requirements are not fulfilled. As simple as that. Okay. In fact, let me just show you my notes. Sorry. So it's a little blurry. So that's the summary of everything. Aromatic, let me just picture it. So for aromatic, it is the most stable. That's been mentioned earlier. Benzene, an example, is very stable, no? So the requirements are it's supposed to be cyclic, planar, completely conjugated, and it has 4n plus 2 electrons. Or just memorize the list: 2, 6, 10, 14. You basically just add plus 4 every number, okay? For anti-aromatic, it's the same requirements, only that the number of electrons has to be 4 or multiples of 4. So, yeah, considering aromaticity, a compound can be classified in one of three ways. The third one is non-aromatic, not aromatic, literally. It lacks one or more of the following requirements for aromaticity, and it has similar stability to an acyclic compound having the same number of pi electrons. Pi electrons as in the double bonds, no, within the ring. So yeah, what is this? One of them is not cyclic, no, but they do have similar stability. But everybody wants to become aromatic because aromatic is the most stable, no? So that's something you have to know. Benzene cyclohexatriene is an aromatic compound. This one is an example of an anti-aromatic, the cyclobutadiene. It is, what do you call this? It is cyclic, it is planar, it is completely conjugated, as you can see. And does it follow Huckel's rule? Let's count. 1, 2, 3, 4, 4 edges, no? So that's 4 electrons. It is anti-aromatic. This one is an example of non-aromatic because this is not completely conjugated. There has to be a line there, so for it to be completely conjugated. Okay. So another thing. So when it comes to resonance structures, basically of fused ring aromatics, as the number of fused rings increases, the number of resonance structures increases. Let's try to apply that knowledge. So this is one resonance structure of benzene. The other, by the way, the resonance arrow, from what I have seen, this is one of them. You can also rewrite it as this. Either way, it's the same. Another is this, no? So that is for benzene. What if we have naphthalene? Naphthalene is basically this. By the way, let me just verify something. Is naphthalene aromatic? This is an important thing to know. Ah, really? It's not. It's aromatic. Let's try to solve it on our own. Cyclic, yes. Planar, I think so. Completely conjugated, yes. How about, does it follow Huckel's rule? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. Huh. What? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait. think there's something wrong with my drawing. Yeah, there is. My drawing is wrong. It's supposed to be just 10 electrons. My bad. So there's already something wrong in the previous video. I clarified that this kind of compound isn't aromatic. It actually, in fact, is. I just drew it the wrong way. Okay, so it is completely conjugated and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons. It does follow Huckel's rule. Okay, let's try to identify the resonance structures of this compound. So how many fused rings do we have now? We have one additional. So I think there are 3 resonance structures for this, including this one. So we started with benzene. We have 2 resonance structures. We fuse one ring, then we have 3 resonance structures. So when we draw resonance, so after drawing the original image, let's just show arrows. Okay. Okay, that's one of them. And then we shift one more time, the same direction. Okay. Something doesn't look right. Yeah, something doesn't look right, bro. Let me just show the picture. So that's what it looks like. Naphthalene is carcinogenic, by the way. One example is the mothball. I think that's the one you store in a cabinet to prevent any moisture. I think that's the purpose. I don't know. Okay, let's have some sample problems. Basic prediction. Okay, so this is cyclic. Planar, yep. Is it completely conjugated? Yep. Does it follow Huckel's rule? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 electrons. Nope. Oh, sorry, wait. It's 12 electrons, therefore, well, 12 is a multiple of 4. So this is anti-aromatic. Okay. Next example. Okay, so this is cyclic, number 1. Number 2, is it planar? Yep. Is it completely conjugated? Yep. Does it follow Huckel's rule? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I think 14 is in the list. This is aromatic. Next. I don't like drawing this figure, bro. Bruh. Let me just show you the picture. So that figure is anti-aromatic. Okay. Okay. Let's try a few more examples. Okay, I'm actually gonna need the actual material. I can't read my own drawing. One, two, three, four, five, six, 7, 8, 9, 10. Desane. Sorry, cyclodesane. 5, 6, 7, 10. No. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11. Assume every side is symmetrical. Okay. So same instructions, determine if aromatic, non-aromatic, or anti-aromatic. Here, it is completely conjugated. Is it planar? I think so. Is it cyclic? Yes. Does it follow Huckel's rule? 2 electrons? It does. This is aromatic. Okay. Follows Huckel's rule still. Is it planar? Not sure. Sorry, this is not aromatic. We haven't had an example previously that tackled this information. Something that you have to know is that these dots matter when it comes to the Huckel's rule. So 1, 2, 3, 4. You count 4. 4 isn't part of the list. So since it's 4, this is anti-aromatic. How about this? 2 electrons. Cyclic, sure. Completely conjugated, sure. Planar. This has to be aromatic. How about this? This is not completely conjugated. We have 4 electrons. Is this planar? I think so. Is this cyclic? Yes. This is not fulfilled, so this is non-aromatic. How about this? This is not completely conjugated, no? There's a gap over here. Is it planar? I think so. Does it follow Huckel's rule? It does. 10 electrons, including these. Cyclic, yep. Let me ask something. In the meantime, while we're waiting for an answer, let's go to the next chapter. EAS, short for electrophilic aromatic substitution. EAS is the characteristic reaction of benzene. So, for the most part, in general, you will see this in all reactions. A hydrogen atom is replaced by an electrophile. Okay? Going back. So yes, it is affirmed. This compound is not completely conjugated. Therefore, this is a non-aromatic compound. Okay? That's now settled. Let's now proceed to the reactions. So there are 5 electrophilic aromatic substitution reactions. Let's ask ourselves first, what do you mean by electrophilic aromatic substitution? So substitution, that is when we replace hydrogen with an electrophile, no? And aromatic because we're talking about benzenes here. That's the most basic part of a reaction. As in, you'll always see a benzene in a reactant side. In the reactant side. No? So, okay. one thing you have to know about the electrophile is that it really loves electrons. It really likes the negative charge, more specifically. And yeah, that's the reason why it's called electrophilic. So generally, this is how it goes. So plus an electrophile in the process, hydrogen is removed. So in place of the hydrogen here, what you have now is the electrophile. So a substitution has occurred. Okay, let's now list the 5 EAS reactions. So always in the reactant side we'll have something like this, okay? You write hydrogen there for emphasis, although it's already understood that there's a hydrogen there. So the first reaction is called halogenation, EAS halogenation. So always from the word halogen, you replace hydrogen with a halogen. For the most part, from what I've seen, only bromine and chlorine are the halogens that are involved. No? Fluorine, I think, similar to a reason for something else, it's not a good halogen because it's too unstable. I think that's the reason why. Like, it's just gonna be a waste of time when we use fluorine. I think I remember part of it. It's partly because it's too electronegative. It is the most electronegative element in the periodic table, so yeah. Anyways, the catalyst here in halogenation actually depends. If the halogen is bromine, it's supposed to be FeBrt. If the halogen you will use is chlorine, which is rarely used because of the toxic nature of chlorine, chlorination is barely performed. It's very toxic, very dangerous. So for the most part, bromination is more often performed in the lab. So this is FeCl3. So the product is going to be this. Okay? There's something else, but what matters is this only. Okay? So these are two halogenation reactions. Number 2. Number 2 in the list is nitration. So there are two compounds here. One of them is going to be the catalyst, H2SO4. This is hydrogen sulfuric acid. Yeah, it has to be concentrated. This serves as our acid. I think HNO3 is also an acid, but H2SO4 is our acid in this scenario because it's a stronger acid. Okay? And okay, so nitration is what we call this reaction. This is gonna be the catalyst. That's our acid kasi, our Lewis acid. What do you call this? NO2. Okay, so that's basically it. What you form is a nitrobenzene. The only reason that makes nitration useful is you can transform this into aniline. Aniline is the key to many other materials that you can synthesize. No? How can you produce aniline coming from nitrobenzene? You perform reduction, more specifically hydrogenation. Let me just confirm if what I just said is correct. This has already been corrected previously. Yep, it's called hydrogenation. So what do we have in hydrogenation? In this case, there are actually many combinations. No? It could be palladium catalyzed hydrogenation, tin catalyzed hydrogenation together with HCl. There's another one, also with HCl. Iron catalyzed. So this one is tin catalyzed. So any of these three combinations will do. So you basically involve that with nitrobenzene and you produce aniline. By the way, this one is called bromobenzene. This one is chlorobenzene. Okay, so those are the two reactions. Let's move on now to the third. By the way, for each one later, I'll be discussing the mechanism. That's the one of the beefiest parts of this topic. It's pretty long. The good thing is there is something similar, is consistent, that makes it not so difficult to memorize. No, you just need the proper practice to actually understand what's going on. Then you'll eventually memorize. And that's what's exactly what I'm gonna do for the remaining time. Then we'll move on to another topic afterwards. Okay, so third is this is Friedel-Crafts acylation. So what are the reagents? We're gonna involve AlCl3, that's gonna be our catalyst. We want to add Cl we want to add an acyl group. No, so that's this is what an acyl group looks like. It technically is a kind of ketone from this. This is a ketone, ORCR. Later on, we can convert this ketone into, I think it's also by reduction. You convert it to produce what? Let me check my notes. That's one of the reactions that we'll talk about later. As early as now, let's talk about it now. Yeah, we perform reduction of acyl benzenes. Acyl benzene is the product that you get from FC acylation. FC is short for Friedel-Crafts. Friedel-Crafts because two people discovered this kind of reaction together with actually the fifth one. I'll discuss the fifth one later. For now, let's stick first with FC acylation. Acylation as in acylation. Okay? That's the spelling. So what we produce is again an acyl benzene. Okay. So this is our acyl group. The acyl benzene is reduced. We can further reduce this so that actually wait, For what reason? Let me talk about that later. Since I haven't discussed number 5 yet. I have to discuss number 5 first before I can talk about this one. Because there is a limitation in what the fifth reaction can do. And that is where FC acylation steps in together with the reduction that follows, so that you avoid something that you have to avoid with the fifth reaction. We'll talk about that later. Number 4. This is sulfonation. You have an SO3 group. Sorry, SO3. Just SO3. And what is the catalyst? It is also sulfuric acid, but you add Cl. Sorry. It's supposed to be H. You add SO3. Just SO3. Then the product is going to be something similar. It's one of the common names that I advised you to memorize. It is benzene sulfonic acid. I think. Let me just check if my memory is correct. Yep, that is correct. Benzene sulfonic acid. So this is the product of sulfonation. Nothing follows. Let's move on to the fifth reaction. So this one is also called Friedel-Crafts, but this time alkylation. So you add an alkyl group. So this is what you get. Okay. So what is the requirement for this reaction? You need an alkyl chloride. This one. And AlCl3 as the catalyst. Okay. So it's important to memorize these reactions. They will not be provided, in the exam. At least for us, chemical engineering students. Okay. For clarifications, there are some things you have to know. I'm gonna emphasize these. So this is an acyl group, no? It's a requirement for FC acylation. And this is a sulfonic acid group, the product substituent you see in sulfonation. There is also the alkyl group, simply just an R. Okay? So, what do we do now? Okay, so let's start now with the mechanism. By the way, Lewis acid catalysts. Let me just emphasize them in dark red. Those are the catalysts. Everything that's written below the arrow, reaction arrow, are catalysts. Okay, so you see there's something consistent. It's not hard to memorize. For nitration and sulfonation, reaction 2 and 4, sulfuric acid is the catalyst. It's supposed to be concentrated. And for the Friedel-Crafts reactions, acylation and alkylation, consistently, AlCl3 is a catalyst. Although later on, uh, you will find out that alkylation can be performed without this catalyst. I think there's a catch though. We'll find that out later. I just can't remember. Okay. So mechanism of substitution. Regardless of the electrophile you use, all EAS reactions occur by the same two-step mechanism. So the only difference among the reactions is how the electrophile is going to look like and how it's going to be generated. No? So there is still electrophile generation as in a way, let's say it's a preamble, no? When we compare it to the constitution. Um, Anyways, step 1 is what follows. So this is usually called, this is universally called the formation of the arenium ion. Let me just clarify something. What is the difference between benzene and arene? Arene is the functional group that you call for benzenes. Okay. Formation of arenium ion. So here, once you generated the electrophile, it's already here. First step is the first arrow is gonna be this. So coming from the pi bond, you aim towards the electrophile. As a result, so the double bond disappears. You have a carbocation ion here. This is a hydrogen and the electrophile is over there. Okay, just imagine the arrow as a grabber, no? So, yeah. And then, what is generated after step 1? The arenium ion. It's actually this one. So, an arenium ion is resonance stabilized. In other words, it can be delocalized. The benzene acts as the nucleophile, no? It uses its pi electron to attack the electrophile. So the arrow from the point of negative charge wait. This is the arrow I'm referring to, by the way. Okay. We can apply resonance here. It's important to know so that you know where the electrophile is going to attach. Just to list the possibilities, these are the following. So this is one possibility. So the carbocation ion moves here. And then move one more time. Oh wait, sorry. Yeah, you can't move any further. Let's make this move there. And then the carbocation is right there. So there are 3 possibilities, no, for at least benzene. Okay, so again, this is our arenium ion. It is now formed. Step 2, the last step, fortunately, is about the regeneration of the aromatic ring. For all reactions, it's already clear that there is a catalyst, no? So the catalyst dissolves at the beginning of the reaction, and it is reformed towards the end of the reaction. We'll see that later when we show the mechanism. For now, this is just in general. We're not actually showing any reaction yet. Okay. Actually, let's write the step 2 here already. I don't think we have to put it downstairs. Okay. Regeneration of the aromatic ring. So we need the base. We need something that is basic in the solution. It basically has to contain a lone pair or a negative charge. Something that's also different in every reaction is the base. No? And I think the only way to recognize what that base is for that reaction is by memorization. So okay. This base arrow is going to the hydrogen, no? Base to the hydrogen, and then this bond goes here. Let's say look at one of the resonance structures. What if this is what we have? Let's do that. And then the carbocation is right here. So how do we change the arrow? No? Coming from here, we go here. Okay, see the logic? What if our figure is like this? So this will go here. Wait a minute. I actually am testing the limits. I think this is the limit. Although it is considered a resonance structure, I don't know. Something is off with this structure, although it's considered correct. Just for the sake of consistency, let's avoid that. I don't think again, these are resonance structures. your thinking strategy, you only have a few minutes for the exam. You only consider these two, okay? Whatever works. It already worked earlier. I was just trying to see other possibilities, no? So let's try this. So 2 arrows in step 2. The outcome is going to be so the double bond is seen again, and the hydrogen is gone. It is taken by the base, no? But you don't have to show that anymore. This is what matters. So again, in step 2, in the regeneration of the aromatic ring, earlier we broke it, no? It is regenerated again. So it's the same story for the catalyst. It is regenerated again, but specifically it is, and realistically, it is in a smaller amount for some reason. Okay. The bond to the hydrogen goes back. That's how the double bond is regenerated. There, and ultimately, the aromatic ring is regenerated back. The arenium ion lets go of the hydrogen because it wants to be aromatic again. Remember what's been mentioned earlier? Aromatic compounds are stable. So the tendency is the arenium ion that we just formed wants to become aromatic again, no? In other words, it wants to be stable once again. That's basically the story, okay? Let's now begin with halogenation, the first reaction. So again, let's write the fast version of it. Well, this isn't exactly showing mechanism. Predicting, rather, is a better word. Okay, so for the mechanism, we first always start not in step 1. We start with the electrophile generation. So for electrophile generation, we have Br, no? What we want to substitute. It can hold up to 7 electrons, so there's no charge right now. The catalyst, let's add the catalyst. So these are the key players, no, that are involved in electrophile generation, whatever is here. So where will the arrows point? Arrow from here to here. What's gonna happen is that so you see lone pairs. Arrow will start from there. It will point to the catalyst. Therefore, as a result, this one becomes negative. Because it now holds 8 dots. This one is now FeBr. What is iron in the periodic table? How many? Let me just check. I hope you have your periodic table with you. Iron is in the transition metals. Okay. I think you can basically just get from the information FeBr3, there's no charge. So I think it just holds the right amount of atoms. If it holds 4 now, it's gonna be negative. No? Sorry. This is not separated. So this is 6 electrons, Br becomes positive here. Fe becomes negative. Okay, everything else is neutral. So we have one positive, one negative charge. If we combine them, it becomes neutral. So just as it should be. This is gonna be the source of our electrophile, no? So this is just gonna be a big leaving group. This is gonna be our electrophile. Okay. So we're still gonna write the entire chunk in step 1. Again, step 1 is the formation of the arenium ion. We generate the the benzene attacks the electrophile. Okay, let's rewrite Br Fe Br3. Sorry. Negative, positive. Don't forget the benzene. Show the hydrogen, and then the plus sign. So what are the arrows involved here? Let's look back to our template. So from here, no, one of the double bonds in the ring itself, it goes to this. This bond goes here. Result, the arenium ion is formed. Sorry. Plus Br, and then Fe Br3. This Fe is still negative. Br is now neutral because this bond just countered the positive charge. So for halogenation, this is gonna act as our base in step 2. I just wanna see, can we make this horizontal? Okay, not bad. Okay. So that's it. Let's now move on to step 2. Regeneration of the aromatic ring. Is that correct? Yeah. So in step 1, the benzene attacks the electrophile, no? In step 2, the base attacks the hydrogen here. Let's show that. So the negative charge of the base, it is negatively charged or it has lone pairs, no? That's a condition. Where is that? Yeah, this one. So the base is negatively charged. It makes sense for our iron to be negatively charged. We connect it to the hydrogen. The bond that connects to the hydrogen is moved here. Therefore, what you get is that. And then you now have bromine. The hydrogen is taken by this base. Wait a minute. Sorry. Minor correction. The arrow has to come from the bond, not the negative charge. Not sure why, but it happens that we have HBr, this one and this one, combined together, and then FeBr3. So it does make sense. Earlier, the catalyst, this one, was merged to our electrophile, no? And it did many things until it was regenerated back as just FeBr3. So yeah, reformed at the end of the reaction. Okay, I'll give some time to study the reaction. Then we'll proceed to the next. Okay. Next in our list is nitration. Okay, for nitration, again, this is useful because we can reduce its product into an NH2 group, in other words, aniline. Let's write this. So when we apply HNO3 and H2SO4, what we get is NO2. We further reduce this to get aniline. What do we use? H2, PDC, Fe, HCl, SN, HCl. Okay. Okay, so let's start first with the electrophile generation. Let's talk about the HNO3. How do we write HNO3? That's how we draw it, okay? Nothing except that way, no other way. So apparently, nitrogen, in the periodic table, so we have Bal, wait, uh, BCNOFNE. Group 3, group 4, group 5. Nitrogen is maximum 5 electrons. That's why this is positive, because it only has 4 connections. No? And for oxygen here, it is minus because it has 7. Its limit is 6 only. Okay? That's how we write HNO3. Okay? And then HOSO3H. This is how we write. We spread it out like this. And then the actually you might think that this is where we start the arrow. It actually starts here. Not sure why. And then this bond goes here. The result is this is still negative. So we now have a hydrogen. This one is, what do you write? Positive. Nitrogen is still positive. So as you can see, there are two positive charges very close to each other. It cannot stand that. So it's gonna turn into what? It's gonna turn into our electrophile. No. One thing to note, by the way, water, this is water, is a good leaving group. Yeah, that is going to be our leaving group. And O2, this one, is gonna be our electrophile. No? So let's show that. Sorry. Negative charge to that bond to produce a double bond. We put an arrow here so that we can separate water and NO2. Yeah, wait. Let's see. Yeah, so that's neutral already. Nitrogen, on the other hand, with its two oxygens rather, it's gonna look like this. And two pairs. No. 1, 2, 3, 4. So only 4. It's positively charged. We're not gonna need water anymore, so we don't have to write it, no? It's not part anymore. We don't need it. So hold on to that electrophile. Let's now start with step 1. Step 1 is the formation of the arenium ion. The benzene, specifically the double bond, attacks the electrophile. Let's show that. Okay, so it attacks the positive charge in the nitrogen. So as a result, we lose the double bond and we have NO2 here. No? And now it has no charge. It's neutral. We have a carbocation over there. So that's this is our rhenium ion. Step 2 is finished. We have formed the rhenium ion, and this one was able to attack the electrophile. Step 2, regeneration of the aromatic ring. To achieve that, the base has to attack the hydrogen. What is going to be our base here? The base is gonna be, it's specific eh? HSO4. This is the base. So if you have H2SO4 as your catalyst, the base is HSO4. For halogenation, it's basically your leaving group. No? Here, you cannot say that the leaving group is also the base. It's actually HSO4. So I'll highlight that. Something that you just have to know. You cannot just get it from common knowledge. No? It's very specific. Okay, so back to where we were. Attack the hydrogen, and then this bond goes here. So the aromatic ring is regenerated rather. And now you have H2SO4. It makes sense. If you add H there, you get H2SO4 back. It helps because when you know that the catalyst is gonna be reformed towards the end of the reaction, you have to expect that the catalyst is written exactly the way it is. No? So yeah, I think that's gonna help also in remembering. So if our catalyst here in nitration is H2SO4, it's the same in the story of sulfonation. Yeah, it's a good thing because the base there is also H2SO4. Sorry, HSO4 minus. So I think that narrows down, no? Something when it narrows down our memorization. Let's actually do it now. We will save the best for last, the Friedel-Crafts reactions. Sulfonation. So, as mentioned earlier, we need the H2SO4 as the catalyst, and the electrophile is going to be the, what do you call this? SO3. Yeah, just SO3. And then this becomes SO3H. Benzene sulfonic acid. Okay. So what's the mechanism? Basically, H2SO4 protonates SO3 and a powerful electrophile is generated. Okay. So for electrophile generation, this is gonna be memorable. Kinda looks goofy. I I hope that helps you remember. SO3 is written this way. And again, OSO3H. That is how you write sulfuric acid. So, where is sulfur in the periodic table? BCNOF. Baal. Pabili ng sisig. No problem. Out of stock for closure. S is 6. 6 maximum electrons. This is neutral. So according to the answer key, the arrow points here. Then the arrow points there. There is no charge here. We use any of the double bonds na. Here in nitration. Okay. So either whether it's a lone pair or a double bond, that's where the arrow starts. Yeah, we started with a lone pair. Where did we see that here? No, we didn't see it there. Okay. 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 So, what is the result? So we still retain the rest, but here we have O and then H. Now, sulfur is gonna be positive because it now has 5 connections. It's no longer neutral. How about the other party? It is gonna be HSO4 minus. That is consistent. Sorry. That is consistent. How were we able to form water instead of HSO4 minus here? Maybe let's not question that anymore. Okay. So anything else? No, we don't. This is already final. This is gonna be our base later. No? So, step 1. Formation of the arenium ion. The electrophile is going to attack, the hydrogen of our benzene is going to attack the electrophile. Hydrogen? Did I mention hydrogen? Rather, the double bonds. Huh? Okay, SO3H. Oh, sorry. This one's already absent. Wait, this looks weird. Let's not do this. Let's come from here. The one above. So this one's missing. Carbocation right there. Okay, more like it. So what now? I think we already formed the arenium ion. Now we include our base. Attack the hydrogen. The hydrogen goes here. I mean the bond. So as a result, the aromatic ring is reformed. Hydrogen is gone. The catalyst is reformed. Okay, that's it for sulfonation. Let's now move on to FC acylation. So the Lewis acid AlCl3 catalyzes the FC acylation by acid chlorides. No? Okay, so oh my gosh, this is a lot. Okay, let's make it a little faster. So you need an acid chloride, an acyl group rather. Although it's the same thing in the context of what we're doing right now. So we basically attach it like this, like this, and then HCl is formed. Okay, for the mechanism, generally AlCl3 pulls off a chloride ion to make an acylium ion. This acylium ion constitutes a acyl benzene, which could be reduced by either Clemmensen reduction or Wolff-Kishner reduction for a reason. No, we'll get to that later. Let's now start with the mechanism. Electrophile generation. So we start off with our electrophile. We add it with AlCl3, spread out. Where is chlorine in the periodic table? Chlorine is 7, no? Okay, so neutral. Where is aluminum? 3. Yeah, 3. So this is neutral. What do we do? So from the lone pairs, attack the aluminum. Okay, just one arrow. What happens now is Cl here becomes positive, Al becomes negative. Okay? And then it happens that this one, there's an arrow there. We make a triple bond. Plus Cl, Al, Cl3. This is gonna be our leaving group. this one can be rewritten as RCO. Okay, but we have to go through this first so that we could separate the leaving group from our electrophile, because carbon can only attach to 4 maximum. If we attach 5, that's when it separates. Then for better stability, the more favored form is this, and you only do that once you separate it from the leaving group. And since carbon here only has 3 connections, this is positive. Okay, so that's our electrophile. Let's now proceed to step 1. So you have hydrogen plus your electrophile. You choose the more stable form. Okay, the benzene attacks the electrophile. Okay, so the positive charge is now gone. This is our arenium ion. What's gonna be the base here? So the base apparently is our leaving group. Interesting. Okay. Let's summarize. Sulfonation, the base is HSO4. Same for nitration. For halogenation, it is the leaving group. I think we see a pattern, consistent, although not in everything. For nitration and sulfonation, the base is HSO4 minus. For FC acylation, the base is ClAlCl3. Let's check alkylation. It actually is also ClAlCl3. By the way, Al here is minus. Al can only hold 3 connections, so adding another one makes it negative. Makes sense, because the base is always going to be minus. The minus sign will attack the hydrogen, and the hydrogen will go back to form the double bond. Then we have this one left, plus, start from here. So we have HCl plus AlCl3. AlCl3 is reformed again. No, that's what we're trying to show. Okay, so that is for FC acylation. Let's now move on to FC alkylation. Am I recording? Okay. So, AlCl3, let's say CH3 CCl. So we have CH3 3 plus HCl. So just a heads up, Friedel-Crafts acylation is similar to Friedel-Crafts alkylation in the sense that we also have these as products. But what our focus is this one, no? When we predict, we only write this, okay? So for the mechanism, generally, AlCl3 pulls off a chloride or bromide anion in order to form a carbocation, okay? How do we write this one? I think that's how you write it. Yeah. Okay. So for the electrophile generation, we start first with the electrophile. Let's write the skeletal structure. So Cl here. It's like that, no? Then plus Al spread out, Cl, Cl, Cl. Everything is neutral. So from the lone pair, attack the aluminum. The result, hang on. This will do. Minus plus. Yeah, it's better you write it this way. Actually, write it this way. Cl being at the front. You know, because this one eventually will be our leaving group. Similar, actually it's the same as for the one in acylation. This is gonna be our electrophile. So let's draw a few more arrows. The question is where? So just one arrow. There you go. So the result is you have a carbocation plus Cl AlCl3. This one's negative. That's gonna be our base later. Okay. So step 1, generation of electrophile. Sorry, of the arenium ion. And the benzene is going to attack the electrophile. Again, what's our electrophile? This carbocation, no? Sorry. There you go. And then it's like that. Don't forget the plus. Did I forget that earlier? Nope. Okay, so this is our arenium ion. We now apply the base, which is Cl AlCl3 minus attack the hydrogen. This one goes here. So we have HCl plus AlCl3. Okay. Hold up. Sorry. It's supposed to be, so this one, this, and this. You produce a certain line that's beside this. That's besides this one. No? What I assumed is that you just stick the carbocation there. It's not like that. This one, and then that's when you start counting how many lines this figure has. So you have 1, 2, 3. Okay, aside from that, everything is correct. We're now done discussing the mechanisms of the 5 reactions. So I mentioned earlier that FC alkylation can happen without AlCl3 under the condition that the functional groups involved are able to form carbocations, no? So you have to watch out for carbocation rearrangements. That's something that I'm not prepared for. I'll check out carbocation arrangements tomorrow. I don't have time tonight. Let's have these examples. So what if you have this? You want to predict the starting materials, or like the starting reagents. And the catalyst is AlCl3. How would you predict? Of course, you would start simply with a benzene. And the electrophile is going to be the alkyl halide, no? And then don't forget the Cl. So these are gonna be your starting reagents for this kind of product. How about this? How about this? This is definitely not primary alkyl halide. Again, this is still gonna be under the catalyst AlCl3. So we start with our good old benzene ring, and we add Cl and then this one. So it's always gonna be chlorine, no? For Friedel-Crafts reactions in general. We don't involve bromine. Bromination is only for halogenation. How about a few more examples? So, how would you form, what would be the starting reagents for this kind of product? Again, start with your good old benzene, Cl, and then basically redraw that. Okay, I think that's good. That's correct. Next. This one is an acyl group. Yeah, it is an acyl group. So this one's definitely a FC acylation. This one is basically just FC alkylation. Okay, so let's now move on to the regiochemistry of EAS. Let's have toluene for an example. So we have Br2, FeBr3. There are wait a minute. There is a table for this. CH3 happens to be one of the activating groups. Rather, it's an ortho para director. What's that supposed to mean? I'll discuss in a while. Just know that CH3, or basically our group, is an ortho para director. We can draw this when we brominate. We can draw the product in these three ways. So in the ortho position, meta position, and para position. But because CH3 is an ortho para director, toluene, our figure, our compound, favors the ortho and para position. No? There are only trace amounts in the meta position. But for to be more specific, para is the most favored, no? At least usually, as opposed to ortho. That's why in multi-step synthesis, from my experience, you have to, after producing two possible products, ortho and para position, showing ortho and para position, there's a part where you isolate the para product because that is the most favored, no? So we'll see to that later if I'm gonna finish everything in this video. This video is almost 2 hours, so probably in the next one. Okay, some important things to note. Substituents that favor ortho para substitution are the following. So we have substituents with lone pairs. For example, phenol. Oxygen has lone pairs. No? So is chlorobenzene. Okay. Also, at the same time, it is important to note that alkyl groups also favor ortho para substitution, even if they don't have lone pairs to stabilize the positive charge. Instead, what they do is they donate electron density via hyperconjugation. Although I'm not going to elaborate more on that. It's an advanced topic, no? Hyperconjugation. Just think that all our groups donate electron density to an rhenium ion. Okay? Our group, like I said earlier, is a paradirector. For as long as this R group is an alkyl group. Okay? Alkyl substituents, for example, something as simple as toluene, the example we exhibited earlier. What if it had a tertiary alkyl or a tert-butyl? This is isopropyl, by the way. So yeah. Alkyl substituents, essentially, they favor ortho-para substitution because they stabilize the carbocation ion in the rhenium ion intermediate. Okay. How about substituents that favor the meta substitution? Meta directors, basically. So wait. So number one in the list, substituents without lone pairs. Except alkyl groups. Alkyl groups are exempted. Once you hear the word alkyl group, they're automatically orthopara, even though they don't have lone pairs. Okay. They favor the meta substitution because ortho and para substitution lead to destabilized arenium ions. Okay. Let's have an example to prove the point. So this is a substituent without lone pair. We assemble with an electrophile. What do we get? We have three resonance structures for this, no? One of them, so yeah, so this is what happens. Positive charges become so close to each other now. What's another resonance structure? This one is in the ortho position. This one is in the meta position. So as you can see, they're far from each other. Yeah, sounds about right. So yeah, positive charges become close to each other. Again, substituents without lone pairs favor the meta substitution. Okay. So yes, resonance structures where CO and CN double banda are shown. All of them disfavor orthopara. They favor meta. So okay. So now, how do we discern meta and para ortho? 3:38, 4 a.m. I hope I can wrap up by 4. Yeah, I seriously have to sleep as soon as possible. What? Time is so fast. 1, 2, 3, 4, 5. Okay. I have to end the video very soon. I'll just continue studying tomorrow. Let's just finish what I can. So lone pair donor resonance. Donor effects outcompete inductive effects. Let's make it fast. I'll get to this tomorrow. I don't really get this part yet, to be honest. If it takes me a while to teach it properly, and yeah, that's already a sign that I'm not really ready for that topic yet. But for the rest, it's pretty much just a highway. Let me just use my camera. So, this is the summary, no, of reactivity and directing effects. This is gonna be provided in the exam. So the only thing you have to do, and it's already pretty generous if you think about it, is that you have to know how to use it, no? So it basically summarizes the rules earlier. So substituents that favor ortho and para substitution are substituents with lone pairs, and substituents that are alkyl, no? For those that favor the para, they are the ones that don't have lone pairs, no? So it's all summarized in this table. These are the activating groups: NH2, anilines, phenols, OR, NHCOR. R group, like I said, this is an ortho para director, no? Everything here, all the way until halogens. Halogens are ortho para directors. Okay? They favor the ortho and para position. So, this is the region from here to here where Friedel-Crafts is useful. No? You cannot say that Friedel-Crafts is useful anywhere else. Contrary to popular belief, you might think that since this one is considered activating group, phenols and anilines more specifically, and they are also para directors, it doesn't mean that they are also, it doesn't mean that FC is also useful, no? It's because of their characteristic of being highly activating. So it has something to do with over-halogenation. Hang on. Yes. The rule on over-activated anilines and phenols. They show they are highly reactive. Is that how you call it? They are highly activating. So yeah, let me talk about this now. Phenols over-halogenate unless you fulfill a certain condition. You leave out the FeX3 catalyst. No? So, for example, here, the OH, if you use FeCl3 as a catalyst and your substituent is a phenol, this one Cl2, this is what happens. So these are the ones written in green. Those arrows point out the possible positions for your products. No? So Cl is a halogen, right? So it favors ortho and para position because it is an ortho para director. So these are the possible positions: ortho to OH, para to OH. Each position is filled with chlorine. That's what you mean by over-halogenation. you end up with chlorine in all carbons where the reaction is possible. So in organic chemistry too, this is basically useless. We don't want these reactions because you want to control the reaction. If only one chlorine is to be assembled, it should only be one. You want control over the reaction. Okay? So if you leave out the FeX3 catalyst, so let's just say you added bromine. Bromine, Cl, same thing. They're both halogens. The only difference is that you left out the FeX3 catalyst. What happens is, well, overhalogenation is prevented. You have your ortho and para product. So the absence of the FeX3 catalyst in a phenol is equal to the absence of any overhalogenated product. Okay, so that's clarified already. How about this? Aniline and derivatives overhalogenate unless one of the R groups is a carbonyl. Okay, that condition is very specific. Yeah. So this is what happens if your aniline is mixed together with, so you have your FeBr3 catalyst and your bromine. It overhalogenates. I need the clarification on this part, actually. Unless one of the R groups is a carbonyl. Carbonyl, this is a meta director. Anyways, let's go back to the table. So, what else? Okay. So those are the para-ortho directors above. Activating groups, what does that mean? They try to donate electron density to the benzene. Activating, as in, they make benzene react faster. In other words, they increase the rate of the EAS. So these come out on top, the anilines and phenols. Because they are so activating, there is a tendency to overhalogenate. Again, remember, for phenols, if you leave out the FeX3 catalyst, you prevent overhalogenation. In anilines, if you add an R group as a carbonyl, if one of the R groups is a carbonyl, you prevent overhalogenation. Okay? Okay. So, what's below the table? We have the activating groups. As you might have noticed, everything here, from here to here, is a carbon. No, this one is a carboxyl group, carboxylic acid. I think this one is aldehyde. I'm not sure. CHO. NO2, the nitro group is here, as well as the SO3H. This is the substituent attached to the product of sulfonation. NR3. Okay. So you use this table to determine which groups react faster. So it's actually ranked, no? From lowest to highest, increasing rate of reaction. No? So meta directors, electrons would be directed to a position meta to that substituent. For the activating groups, everything here, they pull electron density from the benzene. In other words, they are very electronegative. They make the benzene react slower. In other words, they decrease the rate of EAS. So, that's basically everything here is, I think it's already been discussed. Okay. Okay. So yes, how do you use the table? Nitro groups, for example, are meta directors. It does not mean though that nitro groups always end up meta. You have to consider if only the NO2 group were there first, the next substituent will end up in the meta position. If the NO2 group is just going to be added, um, it's not supposed to be meta, no? So for example here, Cl, actually what is this reaction? This is nitration, no? But we already have Cl as our substituent. So Cl is a halogen. It is an ortho paradirector. You don't write the product like this. This one, the substituent formed is gonna be NO2. NO2 is gonna be written in the ortho and para position. That's what it means. Okay? So all activating groups are ortho para directors. All halogens are deactivating, and they are ortho para directors because they are very electronegative. But they activate the benzene because they have a lone pair. Okay. So yeah, they have a lone pair, they are activating. What are special rules for the Friedel-Crafts reactions? So this is very important, no, to consider when you are dealing with multi-step synthesis, one of the most difficult topics in Chem II. So there are many rules that you have to consider. I think this is everything, or at least most of them. So you cannot perform FC acylation or alkylation, basically the two reactions under FC, on a ring that already has a meta director. For example, you performed nitration, and this is your product already. If you want to perform FC acylation or alkylation, you cannot, because NO2 here is already a meta director. See, you could say the same with the product of sulfonation. So FC reaction is not allowed. It will not work because benzene is too deactivated to attack the carbocation. That's the explanation behind it. And there are no Friedel-Crafts on anilines. It will attack AlCl3 instead of the electrophile. That's the tendency. And it's not hard to remember that because aniline is a result of nitration. Once you reduce its product, nitrobenzene. Okay? If you synthesize a benzene with two substituents, you have to decide which substituent is gonna go first. Okay? And the rules will tell you, no? Usually, because of this rule, nitration happens second. Something else happens first. And you might have guessed one of the options is you perform these first, then nitration. Okay? So these are already I have to have this checked tomorrow. I'm not sure if my answers here are correct. But the rules are the greater the directing strength, the stronger the activating group, the higher the rate of EAS. It's a trend. So the higher it is located in the table, the higher rate of EAS and the greater its directing strength. And if you consider steric effect, it doesn't matter as much as directive effect, although you still have to consider this. Okay? Sorry, we're on the time crunch. I could explain a lot more on that part, but I need to sleep already in a few minutes. I'll get to these tomorrow. Limitations, no. This is something that I mentioned earlier. So if you have a primary alkyl halide, you cannot perform FC alkylation on it because the primary alkyl group is too unstable. You can perform FC alkylation if your alkyl halide were secondary or tertiary. But if it's primary, what you do is FC acylation, then reduction. Okay, so this is the kind of question you'll expect in the exam. So you start with this. This is the product. What you're gonna be asked to do is predict what's the entire process, but not really mechanism. Just you have to think backwards. Example here, you have two substituents. What's gonna be? I think there are two steps here, no? Yeah, two steps. So you start first with benzene. Which are you gonna perform first? Okay, you attach CH3 there. And then you perform nitration. Because if you perform nitration first, you can no longer perform FC alkylation. That's what I mean. So there's a reason why nitration came second. Because you cannot add this anymore if nitration happened first. And here, like I said earlier, we're given two products. We already have two products, although only the para is going to be the final answer. So this one. I think it has something to do with the steric effect because CH3 is close to NO2 in the ortho position. But if they are in the para, then steric effect wise, there's much less steric effect in a para position. Yeah, okay. Okay, so these are just limitations of EAS reactions. Okay. I'm gonna have to study this tomorrow, the rules. Something that's not so familiar to me yet. But this part is familiar already. So these are the 4 reactions involving the benzene substituents. So we first have bromination coming from having benzylic CH bond. If you perform bromination, so Br2, under the presence of heat or light, or N-bromosuccinate, I think that's how you pronounce this, NBS, together with light or peroxide, you produce a benzylic bromide. So what changes? One of the hydrogens here becomes a bromine. That's basically it. Not really sure the relevance of that reaction, but yeah. The one below, however, is something actually useful. We have a benzene and an alkyl group. If we add KMNO4, we turn it into benzoic acid. Remember, this is the figure for benzoic acid. So regardless of what your starting compound is, for as long as it has at least one benzylic CH bond, it turns into benzoic acid. This is something that I'm really familiar with now. This one I still need to study a bit more. No reaction will happen if in case everything here is just benzylic carbon. Look, there's just carbon everywhere. Compared to here, there are hydrogens attached immediately. Okay, so bromination cannot happen if this is the case. How about this? Reduction of alkyl benzene. I've mentioned this a few times already. You do this Clemensen reduction and Wolff-Kishner reduction, so that coming from FC acylation, the ketone that it produces becomes reduced into an alkyl benzene. No? So like you used to have an oxygen at the top, it gets converted into hydrogens at the top. No? That's basically it. And there are two kinds of reduction. They do the same thing, only that Wolff-Kishner is more efficient now. So why bother with Clemensen? I don't know. The reason why Clemensen reduction isn't good is because there are many side reactions that happen, no? And it's more dangerous. So this is more efficient, Wolff-Kishner. Hydrazine plus any base that contains a hydroxide, for example, OH, and then you need heat. Heat represented as a triangle. So this one cannot be synthesized by FC alkylation because you will encounter carbocation rearrangement. So these reductions solve the limitation of FC alkylation. FC alkylation followed by FC alkylation. Allows installation of primary alkyl groups in benzene. I'm gonna have to fact check this because as far as I understand, it's supposed to be acylation. Yes, because by definition, ketones formed as products of FC acylation can be reduced. It's not referring to the products of alkylation. I think there's a typo here. This is supposed to be acylation. I need help when it comes to the carbocation rearrangement. So yes, this is the one. Acylation, then reduction by Wolff-Kishner. This is your product. Basically, you remove the oxygen. This is what you have left. So for the reduction of nitrobenzenes, I think this is the last reaction. Yeah, this is the last. Useless, this is the one I was talking about. So after you produce your nitrobenzene from nitration, this is said to be useless. You convert it into useful NH2 group by reduction. So more specifically, hydrogenation type of reduction. These are the catalysts, no? Palladium catalyzed hydrogenation, iron catalyzed, tin catalyzed. Basically, you turn nitrobenzene into aniline. Okay, that's it. And this one is multi-step synthesis. I'll do this tomorrow. I gotta go. Before that, do I have anything else here that's important? Yeah, I think that's it. I'll end the video. Bye bye.